All right, so I'm going to be completing the entire machine learning course or supervised machine learning course from Coursera, taught by Andrew and G. Stop sharing that. My bad. Okay, so basically this is the course, and it's 2 hours and 2 hours and 7 minutes, the entire course. But I do have some sort of idea about machine learning and supervised machine learning and classification and regression, so I don't think I'll be needing that much time to understand what's being taught to me in the videos. And the introductory videos is something I can skip on. So 2 hours and 7 minutes. I've given myself 3 hours in case I come across something that I don't fully understand. To give myself 3 hours is the reason was to have a little buffer. So the attempt is to finish this entire course in 3 hours, and yeah, let's get to it. I have some watermelon here. All right, let's go. Let me just check if it's working. Share this. Oh wait, let me just yep. Hello. Hello. Okay. Okay, we can start. Yeah. So I'm just going to quickly go through this, and then going to go through this, and then this is where the actual machine learning starts. So let's just continue.
So, supervised learning algorithms learn to predict input output or X to Y mappings. And in the last video, you saw that regression algorithms, which is a type of supervised learning algorithm, learns to predict numbers out of infinitely many possible numbers. There's a second major type of supervised learning algorithm called a classification algorithm. Let's take a look at what this means. Take breast cancer detection as an example of a classification problem. Say you're building a machine learning system so that doctors can have a diagnostic tool to detect breast cancer. This is important because early detection could potentially save a patient's life. Using a patient's medical records, your machine learning system tries to figure out if a tumor, that is a lump, is malignant, meaning cancerous or dangerous, or if that tumor, that lump, is benign, meaning that, it's just a lump that isn't cancerous and isn't that dangerous. Some of my friends have actually been working on this specific problem. So maybe your dataset has tumors of various sizes, and these tumors are labeled as either benign, which I will designate in this example with a 0, or malignant, which I'll designate in this example with a 1. You can then plot your data on a graph like this, where the horizontal axis represents the size of the tumor, and the vertical axis takes on only two values, 0 or 1, depending on whether the tumor is benign, 0, or malignant, 1. One reason that this is different from regression is that we're trying to predict only a small number of possible outputs or categories. In this case, two possible outputs, 0 or 1, benign or malignant. This is different from regression, which tries to predict any number out of the infinitely many number of possible numbers. And so the fact that there are only two possible outputs is what makes this classification. Because there are only two possible outputs or two possible categories in this example, you can also plot this data set on a line like this, where now I'm going to use two different symbols to denote the category, using a circle and O to denote the benign examples and a cross to denote the malignant examples. And if a new patient walks in for a diagnosis and they have a lump that is this size, then the question is, will your system classify this tumor as benign or malignant? It turns out that in classification problems, you can also have more than two possible output categories. Maybe your learning algorithm can output multiple types of cancer diagnoses if it turns out to be malignant. So let's call two different types of cancer, type 1 and type 2. In this case, the algorithm would have three possible output categories it could predict. And by the way, in classification, the terms output classes and output categories are often used interchangeably. So when I say class or category when referring to the output, it means the same thing. So to summarize, classification algorithms predict categories. Categories don't have to be numbers. It could be non-numeric. For example, it can predict whether a picture is that of a cat or a dog. And it can predict if a tumor is benign or malignant. Categories can also be numbers like 0 or 1 or 0 or 1 or 2. But what makes classification different from regression when you're interpreting the numbers is that classification predicts a small, finite, limited set of possible output categories, such as 0, 1, and 2, but not all possible numbers in between, like 0.5 or 1.7. In the example of supervised learning that we've been looking at, we had only one input value, the size of the tumor. But you can also use more than one input value to predict an output. Here's an example. Instead of just knowing the tumor size, say you also have each patient's age in years. Your new dataset now has two inputs, age and tumor size. Plotting this new dataset, we're going to use circles to show patients whose tumors are benign and crosses to show the patients with a tumor that was malignant. So when a new patient comes in, the doctor can measure the patient's tumor size and also record the patient's age. And so given this, how can we predict if this patient's tumor is benign or malignant? Well, given a dataset like this, what the learning algorithm might do is find some boundary that separates out the malignant tumors from the benign ones. So the learning algorithm has to decide how to fit a boundary line to this data. The boundary line found by the learning algorithm would help the doctor with the diagnosis. In this case, the tumor is more likely to be benign. From this example, we've seen how two inputs, the patient's age and tumor size, can be used. In other machine learning problems, often many more input values are required. My friends who work on breast cancer detection use many additional inputs, like the thickness of the tumor clump, uniformity of the cell size, uniformity of the cell shape, and so on. So, to recap, supervised learning maps input X to output Y, where the learning algorithm learns from the quote right answers. The two major types of supervised learning are regression and classification. In a regression application, like predicting pregnancy pulses, the learning algorithm has to predict numbers from infinitely many possible output numbers. Whereas in classification, the learning algorithm has to make a prediction of a category out of a small set of possible outputs.
Ooh, question. Supervised learning is when we give our learning algorithm the right answer, Y, for each example you learn. Bruh. What's wrong with me? First try.
So you now know what is supervised learning, including both regression and classification. I hope you're having fun. Next, there's a second major type of machine learning called unsupervised learning. Let's go on to the next video to see what that is. After supervised learning, the most widely used form of machine learning is unsupervised learning. Let's take a look at what that means. We've talked about supervised learning, and this video is about unsupervised learning. But don't let the name unsupervised fool you. Unsupervised learning is, I think, just as super as supervised learning. When we're looking at supervised learning in the last video, we called it look something like this. In the case of classification problem, each example was associated with an output label. Is that this clustering algorithm figures out on its own which words suggest that certain articles are in the same group. What I mean is specific gene active. And what you can do is segmentation found if you distinct. This is a clustering that our team used as well. And besides clustering, there are other types of unsupervised learning as well. Let's go on to the next video to take a look at some other types of unsupervised learning algorithms. In the last video, you saw what is unsupervised learning and you also learned about dimension. You check your supervised learning examples.
Of the following examples, which one would you address using given a database of customer data after any disparate market segments? Given a data set of let's give a set of news articles found on the web, group them into a set of articles based on the same story. Huh?
News and Hangout example that you saw in the last video. And so you can approach that using a clustering algorithm to group news articles together. So that would use unsupervised learning. The market segmentation example that I talked about a little bit earlier, you can do that as an unsupervised learning problem as well, because you can give your algorithm some data and ask it to discover market segments automatically. And the final example on diagnosing diabetes. Well, actually, that's a lot like our breast cancer example from the supervised learning videos. Only instead of benign or malignant tumors, we instead have diabetes or not diabetes. And so you can approach this as a supervised learning problem, just like we did for the breast tumor classification problem. Even though in this and the last video, we've talked mainly about clustering, in later videos in this specialization, we'll dive much more deeply into anomaly detection and dimensionality reduction as well. So that's unsupervised learning. Before we wrap up this section, I want to share with you something that I find really exciting and useful, which is the use of Jupyter notebooks in machine learning. Let's take a look at that in the next video. So far in the videos, you've seen supervised learning and unsupervised learning, and also to implement these experiments, data, simplify it, ask for every single one of them. You don't have to do them at all if you don't want to. See, when you go to the first optional lab, feel free to scroll up and down cell, which looks like that will also convert it back to this, and then see what the code actually in a Jupyter notebook. I'll spend a lot of hours playing around in Jupyter notebooks, and so I hope you have fun with them too. And after that, I look forward to seeing you in the next video, where we'll take the supervised learning problem and start to flesh out our first supervised learning algorithm. I hope that'll be fun too, and look forward to seeing you there.
Is that will expose some of the tools that are used in this. What's going on? Bruh. Next. Start assignment. Okay. Which are two common types of supervised learning? Regression, classification. Which of these is the type of unsupervised learning? Clustering. Submit. Which of these is a type? More. Where am I stuck? Clustering. Bruh. Okay.
In this video, we'll look at what the overall process of supervised learning is like. Specifically, you see the first model of this course, a linear regression model. That just means fitting a straight line to your data is probably the most widely used learning algorithm in the world today. And as you get familiar with linear regression, many of the concepts you see here will also apply to other machine learning models that you see later in this specialization. Let's start with a problem that you can address using linear regression. Say you want to predict the price of a house based on the size of the house. This is the example we seen earlier this week. We're going to use a data set on house sizes and prices from Portland, a city in the United States. Here with a graph where the horizontal axis is the size of the house in square feet, and the vertical axis is the price of the house in thousands of dollars. Let's go ahead and plot the data points for various houses in the data set. Here, each data point, each of these little crosses is a house with a size and a price that it most recently was sold for. Now, let's say you're a real estate agent in Portland, and you're helping a client sell her house, and she's asking you, how much do you think you can get for this house? This data set might help you estimate the price she could get for it. You start by measuring the size of the house, and it turns out that her house is 1,250 square feet. How much do you think this house could sell for? One thing you could do is you can build a linear regression model from this data set. Your model will fit a straight line to the data, which might look like this. And based on this straight line fit to the data, you can kind of see that if the house is 1,250 square feet, it will intersect the best fit line over here. And if you trace that to the vertical axis on the left, you can see the price is maybe around here, say about $220,000. So this is an example of what's called a supervised learning model. We call this supervised learning because you are first training your model by giving it data that's the right answers. Because you give the model examples of houses with both the size of the house as well as the price that the model should predict for each house. Where here, the prices, that is, the right answers, are given for every house in the dataset. This linear regression model is a particular type of supervised learning model. It's called a regression model because it predicts numbers as the output, like prices in dollars. Any supervised learning model that predicts a number, such as 220,000 or 1.5 or negative 33.2, is addressing what's called a regression problem. So linear regression is one example of a regression model, but there are other models for addressing regression problems too. And we'll see some of those later in course 2 of this specialization. And just to remind you, in contrast with the regression model, the other most common type of supervised learning model is called a classification model. A classification model predicts categories or discrete categories, such as predicting if a picture is of a cat, meow, or a dog, woof, or if given a medical record, it has to predict if a patient has a particular disease. You see more about classification models later in this course as well. So as a reminder about the difference between classification and regression, in classification, there are only a small number of possible outputs. If your model is recognizing cats versus dogs, that's 2 possible outputs. Or maybe you're trying to recognize any of 10 possible medical conditions in a patient. So there's a discrete, finite set of possible outputs. We call it a classification problem, whereas in regression, there are infinitely many possible numbers that the model could output. In addition to visualizing this data as a plot here on the left, there's one other way of looking at the data that would be useful, and that's a data table here on the right. The data comprises a set of inputs. This would be the size of the house, which is this column here. It also has outputs. You're trying to predict the price, which is this column here. Notice that the horizontal and vertical axes correspond to these 2 columns, the size and the price. And so if you have, say, 47 rows in this data table, then there are 47 of these little crosses on the plot of the left, each cross corresponding to 1 row of the table. For example, the first row of the table is a house with size 2,104 square feet, so that's around here. And this house sold for $400,000, which is around here. So this first row of the table is plotted as this data point over here. Now, let's look at some notation for describing the data. This is notation that you find useful throughout your journey in machine learning. As you increasingly get familiar with machine learning terminology, this will be terminology that you can use to talk about machine learning concepts with others as well, since a lot of this is quite standard across AI. You'll be seeing this notation multiple times in the specialization, so it's okay if you don't remember everything the first time through. It will naturally become more familiar over time. The dataset that you just saw and that is used to train the model is called a training set. Note that your client's house is not in this dataset because it's not yet sold, so no one knows what its price is. So to predict the price, and so here, y is the price of the house. And for the first training example, this is equal to 400. So y equal to a specific training example. This will correspond to a specific row in this table on the left. I'm going to use the notation x superscript in parentheses I, comma, y superscript in parentheses I. This superscript tells us that this is the I training example, such as the first, second, or third up to the 47th training example. I here refers to a specific row in the table. So for instance, here is the first example when I equals 1 in the training set. And so x superscript 1 is equal to 2. A training set is like. That's what's the standard notation for describing this training set. In the next video, let's look at what it'll take to take this training set you just saw and feed it to a learning algorithm so that the algorithm can learn from this data. We'll see that in the next video. Let's look in this video at the process of how supervised learning works. Supervised learning algorithm will input the data set, and then what exactly does it do and what does it output? Let's find out in this video. Recall that a training set in supervised learning includes both the input features, such as the size of the house, and also the output targets, such as the price of the house. The output targets are the right answers that the model will learn from. To train the model, you feed the training set, both the input features and the output targets, to your learning algorithm. Then your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take a new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the the convention is that y hat is the estimate or the prediction for y. The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell their hulls, well, the true price of the hulls is unknown until they sell it. So your model f, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. So your function can be written as f subscript w comma b of x equals, I'm going to use w times x plus b. I'll define w and b soon, but for now, just know that w and b are numbers, and the values chosen for w and b will determine the prediction y hat based on the input feature x. So this fwb of x means f is a function that takes x as input, and depending on the values of w and b, f will output some value of a prediction y hat. As an alternative to writing this fw comma b of x, I'll sometimes just write f of x without explicitly including w and b in the subscript. It's just a simpler notation, but means exactly the same thing as fwb of x. Let's plot the training set on the graph where the input feature x is on the horizontal axis and the output target y is on the vertical axis. Remember, the algorithm learns from this data and generates a best fit line, like maybe this one here. This straight line is the linear function fwb of x equals w times x plus b. Or more simply, we can drop w and b and just write f of x equals wx plus b. Here's what this function is doing. It's making predictions for the value of y using a straight line function of x. So you may ask, why are we choosing a linear function, where linear function is just a fancy term for a straight line, instead of some nonlinear function like a curve or a parabola? Well, sometimes you want to fit more complex nonlinear functions as well, like a curve like this. But since this linear function is relatively simple and easy to work with, let's use a line as a foundation that will eventually help you to get to more complex models that are nonlinear. This particular model has a name. It's called linear regression. More specifically, this is linear regression with one variable, where the phrase one variable means that there's a single input variable or feature x, namely the size of the hulls. And another name for a linear model with one input variable is univariate linear regression, where uni means one in Latin, and where variate means variable. So univariate is just a fancy way of saying one variable. In a later video, you also see a variation of regression, where you want to make a prediction based not just on the size of the hulls, but on a bunch of other things that you may know about hulls, such as number of bedrooms and other features. And
Whoa. For linear regression, the model is represented by which of the following y hat? Submit. Bro, what is wrong with me?
by the way, when you're done with this video, there is another optional lab. You don't need to write any code. Just review it, run the code, and see what it does. That will show you how to define in Python a straight line function. And the lab will let you choose the values of w and b to try to fit the training data. You don't have to do the lab if you don't want to, but I hope you play with it when you're done watching this video. So that's linear regression. In order for you to make this work, one of the most important things you have to do is construct a cost function. The idea of a cost function is one of the most universal and important ideas in machine learning, and is used in both linear regression and in training many of the most advanced AI models in the world. So let's go on to the next video and take a look at how you can construct a cost function.
I'm just going to skip the lab.
In order to implement linear regression, the first key step is for us to define something called a cost function. This is something we'll build in this video. And the cost function will tell us how well the model is doing so that we can try to get it to do better. Let's look at what this means. Recall that you have a training set that contains input features x and output targets y. And the model you're going to use to fit this training set is this linear function, fwb of x equals w times x plus b. To introduce a little bit more terminology, the w and b are called the parameters of the model. In machine learning, parameters of a model are the variables you can adjust during training in order to improve the model. Sometimes you also hear the parameters w and b referred to as coefficients or as weights. Now, let's take a look at what these parameters w and b do. Depending on the values you've chosen for w and b, you get a different function, f of x, which generates a different line on the graph. And remember that we can write f of x as a shorthand for fwb of x. We're going to take a look at some plots of f of x on a chart. maybe you're already familiar with drawing lines on charts, but even if this is a review for you, I hope this will help you build intuition on how W and B, the parameters, determine F. When W is equal to 0 and B is equal to 1.5, then F looks like this horizontal line. In this case, the function f of x is 0 times x plus 1.5, so f is always a constant value. It always predicts 1.5 for the estimated value of y. So y hat is always equal to b, and here b is also called the y-intercept because that's where it crosses the vertical axis or the y-axis on this graph. As a second example, if w is 0.5 and b is equal to 0, then f of x is 0.5 times x. When x is 0, the prediction is also 0, and when x is 2, then the prediction is 0.5 times 2, which is 1. So you get a line that looks like this. And notice that the slope is 0.5 divided by 1. So the value of w gives you the slope of the line, which is 0.5. And finally, if w equals 0.5 and b equals 1, then f of x is 0.5 times x plus 1. And when x is 0, then f of x equals b, which is 1. So the line intersects the vertical axis at b, the y-intercept. Also, when x is 2, then f of x is 2. So the line looks like this. Again, the slope is is 0.5 divided by 1, so the value of w gives you the slope, which is 0.5. Recall that you have a training set, like the one shown here. With linear regression, what you want to do is to choose values for the parameters w and b, so that the straight line you get for the function f somehow fits the data well, like maybe this line shown here. And when I say that the line fits the data, visually you can think of this to mean that the line defined by f is roughly passing through or somewhat close to the training examples as compared to other possible lines that are not as close to these points. And just to remind you of some notation, a training example, like this point here, is defined by x superscript I, y superscript I, where y is the target. For a given input xi, the function f also makes a predicted value for y. And the value that it predicts for y is y hat I, shown here. For our choice of a model, f of xi is w times xi plus b. Stated differently, the prediction y hat I is f of wb of xi, where for the model we're using, f of xi is equal to wxi plus b. So now the question is, how do you find values for w and b so that the prediction y hat I is close to the true target yi for many or maybe all training examples xi, yi? To answer that question, let's first take a look at how to measure how well a line fits the training data. To do that, we're going to construct our cost function. The cost function takes the prediction y hat and compares it to the target y by taking y hat minus y. This difference is called the error. We're measuring how far off the prediction is from the target. Next, let's compute the square of this error. Also, we're going to want to compute this term for different training examples I in the training set. So when measuring the error for example I, we'll compute this squared error term. Finally, we want to measure the error across the entire training set. In particular, let's sum up the squared errors like this. We'll sum from I equals 1, 2, 3, all the way up to m. And remember that m is the number of training examples, which is 47 for this data set. Notice that if we have more training examples, m is larger, and your cost function will calculate a bigger number since it's summing over more examples. So to build a cost function that doesn't automatically get bigger as the training set size gets larger, by convention, we will compute the average squared error instead of the total squared error. And we do that by dividing by m like this. Okay, we're nearly there. Just one last thing. By convention, the cost function that machine learning people use actually divides by 2 times m. The extra division by 2 is just meant to make some of our later calculations a little bit neater, but the cost function still works whether you include this division by 2 or not. So this expression right here is the cost function, and we're going to write j of wb to refer to the cost function. This is also called the squared error cost function, and it's called this because you're taking the square of these error terms. In machine learning, different people will use different cost functions for different applications. But the squared error cost include this division by 2 or not. So this expression right here is the cost function. We do that by dividing by m like this. Okay, we're nearly there. Just one last thing. By convention, the cost function that machine learning people use actually divides by 2 times m. The extra division by 2 is just meant to make some of our later calculations a little bit neater, but the cost function still works whether you include this division by 2 or not. So this expression right here is the cost function, and we're going to write j of wb to refer to the cost function. This is also called the squared error cost function, And it's called this because you're taking the error, for example, right, will compute this squared error term. Finally, we want to measure the error across the entire training set. In particular, let's sum up the squared errors like this. We'll sum from I equals 1, 2, 3, all the way up to m. And remember that m is the number of training examples, which is 47 for this data set. Notice that if we have more training examples, m is larger, and your cost function will calculate a bigger number since it's summing over more examples. So to build a cost function that doesn't automatically get bigger as the training set size gets larger, by convention, we will compute the average squared error instead of the total squared error. And we do that by dividing by m like this. Okay, we're nearly there. Just one last thing. By convention, the cost function that machine learning people use actually divides by 2 times m. The extra division by 2 is just meant to make some of our later calculations a little bit neater, but the cost function still works whether you include this division by 2 or not. So this expression right here is the cost function, and we're going to write j of wb to refer to the cost function. This is also called the squared error cost function, and it's called this because you're taking the square of these error terms. In machine learning, different people will use different cost functions for different applications, but the squared error cost function is by far the most commonly used one for linear regression, and for that matter for all regression problems, where it seems to give good results for many applications. So just as a reminder, the prediction y hat is equal to the output of the model f at x, so we can rewrite the cost function j of wb as 1 over 2m times the sum from I equals 1 to m of f of x I minus yi, the quantity squared. Eventually, we're going to want to find values of w and b that make the cost function small. But before going there, let's first gain more intuition about what j of wb is really computing.
The cost function used for linear regression is this. Which of these are the parameters of a model that can be adjusted? W and yes. Submit.
At this point, you might be thinking, we've done a whole lot of math to define the cost function, but what exactly is it doing? Let's go on to the next video where we'll step through one example of what the cost function is really computing that I hope will help you build intuition about what it means if j of wb is large versus if the cost j is small. Let's go on to the next video. We've seen the mathematical definition of the cost function. Now let's build some intuition about what the cost function is really doing. In this video, we'll walk through one example to see how the cost function can be used to find the best parameters for your model. I know this video is a little bit longer than the others, but bear with me, I think it'll be worth it. To recap, here's what we've seen about the cost function so far. You want to fit a straight line to the training data, so you have this model fwb of x is w times x plus b. And here, the model's parameters are w and b. Now, depending on the values chosen for these parameters, you get different straight lines, like this. And you want to find values for w and b so that the straight line fits the training data well. To measure how well a choice of w and b fits the training data, you have a cost function j. And what the cost function j does is it measures the difference between the model's predictions and the actual true values for y. What you see later is that linear regression will try to find values for w and b that make j of wb as small as possible. In math, we write it like this. We want to minimize j as a function of w and b. So now, in order for us to better visualize the cost function j, let's work with a simplified version of the linear regression model. We're going to use the model fw of x is w times x. You can think of this as taking the original model on the left and getting rid of the parameter b, or setting the parameter b equal to 0, so it just goes away. And think of this as a linear regression values for y, j, data well. To measure how well a choice of w and b fits the training data, you have a cost function j. And what the cost function j does is it measures the difference between the model's predictions and the actual true value. And here, the model's parameters are w.
I just saw a Porsche that just filled up gas, and this. That is one heck of a car. It's the second time I'm seeing that Porsche. It's the second time. Or maybe it's the second time I'm seeing a Porsche, because maybe I saw two, I don't know. Okay.
W and b. Now, depending on the values chosen for these parameters, you get different straight lines, like this. And you want to find values for w and b so that the straight line fits the training data well. To measure how well a choice of w and b fits the training data, you have a cost function j. And what the cost function j does is it measures the difference between the model's predictions and the actual true values for y. What you see later is that linear regression will try to find values for w and b that make j of wb as small as possible. In math, we write it like this. We want to minimize j as a function of w and b. So now, in order for us to better visualize the cost function j, let's work with a simplified version of the linear regression model. We're we're going to use the model fw of x is w times x. You can think of this as taking the original model on the left and getting rid of the parameter b, or setting the parameter b equal to 0, so it just goes away from the equation. So f is now just w times x. So you now have just one parameter w, and your cost function j looks similar to what it was before, taking the difference and squaring it, except that now f is equal to w times xi, and j is now a function of just w. And the goal becomes a little bit different as well, because you have just one parameter w, not w and b. So with this simplified model, the goal is to find the value for w that minimizes j of w. To see this visually, what this means is that if b is set to 0, then f defines a line that looks like this. And you see that the line passes through the origin here, because when x is 0, well, f of x is 0 too. Now, using this simplified model, let's see how the cost function changes as you choose different values for the parameter w. In particular, let's look at graphs of the model f of x and the cost function j. I'm going to plot these side by side, and you'll be able to see how the two are related. First, notice that for f subscript w, when the parameter w is fixed, that is always a constant value, then fw is only a function of x, which means that the estimated value of y depends on the value of the input x. In contrast, looking to the right, the cost function j is a function of w, where w controls the slope of the line defined by fw. So the cost defined by j depends on a parameter, in this case, the parameter w. So let's go ahead and plot these functions, fw of x and j of w, side by side, so we can see how they are related. We'll start with a model that is the function fw of x on the left. Here, the input feature x is on the horizontal axis, and the output value y is on the vertical axis. Here's a plot of 3 points representing the training set at positions 1, 1, 2, 2, and 3, 3. Let's take a value for w, say w is 1. So for this choice of w, the function fw looks like this straight line with a slope of 1. Now, what you can do next is calculate the cost j when w equals 1. So you may recall that the cost function is defined as follows. It's the squared error cost function. So if you substitute fw of xi with w times xi, the cost function looks like this, where this expression is now w times xi minus yi. So for this value of w, it turns out that the error term inside the cost function, this w times xi minus yi, is equal to 0 for each of the 3 data points. Because for this data set, when x is 1, then y is 1. When w is also 1, then f of x equals 1. So f of x equals y for this first training example, and the difference is 0. Plugging this into the cost function j, you get 0 squared. Similarly, when x is 2, then y is 2, and f of x is also 2. So again, f of x equals y for the second training example. In the cost function, the squared error for the second example is also 0 squared. Finally, when x is 3, then y is 3, and f of 3 is also 3. In the cost function, the third squared error term is also 0 squared. So for all 3 examples in this training set, f of xi equals yi for each training example I. So f of xi minus yi is 0. So for this particular data set, when w is 1, then the cost j is equal to 0. Now, what you can do on the right is plot the cost function j. And notice that because the cost function is a function of the parameter w, the horizontal axis is now labeled w and not x. And the vertical axis is now j and not y. So you have j of 1 equals to 0. In other words, when w equals 1, j of w is 0. So let me go ahead and plot that. Now let's look at how f and j change for different values of w. W can take on a range of values, right? So w can take on negative values, w can be 0, and it can take on positive values too. So what if w is equal to 0.5 instead of 1? What will these graphs look like then? Let's go ahead and plot that. So let's set w to be equal to 0.5, and in this case, the function f of x now looks like this. Is a line with a slope equal to 0.5. And
I'll be right back.
Let's also compute the cost j when w is 0.5. Recall that the cost function is measuring the squared error or difference between the estimated value, that is y hat I, which is f of xi, and the true value, that is yi, for each example I. So visually, you can see that the error or difference is equal to the height of this vertical line here when x is equal to 1, because this little line is the gap between the actual value of y and the value that the function f predicted, which is a bit further down here. So for this first example, when x is 1, f of x is 0.5. So the squared error on the first example is 0.5 minus 1 squared. Remember, the cost function will sum over all the training examples in the training set. So let's go on to the second training example. When x is 2, the model is predicting f of x is 1, and the actual value of y is 2. So the error of the second example is equal to the height of this little line segment here, and the squared error is the square of the length of this line segment. So you get 1 minus 2 squared. Let's do the third example. Repeating this process, the error here, also shown by this line segment, is 1.5 minus 3 squared. Next, we sum up all of these terms, which turns out to be equal to 3.5. Then we multiply this term by 1 over 2m, where m is the number of training examples. Since there are 3 training examples, m equals 3. So this is equal to 1 over 2 times 3, where this m here is 3. If we work out the math, this turns out to be 3.5 divided by 6. So the cost j is about 0.58. Let's go ahead and plot that over there on the right. Okay. Now let's try one more value for w. How about if w equals 0? What do the graphs for f and j look like when w is equal to 0? It turns out that if w is equal to 0, then f of x is just this horizontal line that is exactly on the x-axis. And so the error for each example is a line that goes from each point down to the horizontal line that represents f of x equals 0. So the cost j when w equals 0 is 1 over 2m times the quantity 1 squared plus 2 squared plus 3 squared, and that's equal to 1 over 6 times 14, which is about 2.33. So let's plot this point where w is 0 and j of 0 is 2.33 over here. And you can keep doing this for other values of w. Since w can be any number, it can also be a negative value. So if w is negative 0.5, then the line f is a downward sloping line like this. It turns out that when w is negative 0.5, then you end up with an even higher cost, around 5.25, which is this point up here. And you can continue computing the cost function for different values of w and so on, and plot these, right? So it turns out that by computing a range of values, you can slowly trace out what the cost function j looks like. And that's what j is. To recap, each value of parameter w corresponds to a different straight line fit of x on the graph to the left. And for the given training set, that choice for a value of w corresponds to a single point on the graph on the right. Because for each value of w, you can calculate the cost j of w. For example, when w equals 1, this corresponds to this straight line fit through the data. And it also corresponds to this point on the graph of j, where w equals 1 and the cost j of 1 equals 0. Whereas when w equals 0.5, this gives you this line, which has a smaller slope. And this line, in combination with the training set, corresponds to this point on the cost function graph at w equals 0.5. So for each value of w, you wind up with a different line, and its corresponding cost j of w. And you can use these points to trace out this plot on the right. Given this, how can you choose the value of w that results in the function f fitting the data well? Well, as you can imagine, choosing a value of w that causes j of w to be as small as possible seems like a good bet. J is the cost function that measures how big the squared errors are, so choosing w that minimizes these squared errors, makes them as small as possible, would give us a good model. In this example, if you were to choose a value of w that results in the smallest possible value of j of w, you'd end up picking w equals 1. And as you can see, that's actually a pretty good choice. This results in a line that fits the training data very well. So that's how, in linear regression, you use the cost function to find the value of w that minimizes j. Or in the more general case, when we had parameters w and b rather than just w, you find the values of w and b that minimize j. So to summarize, exercise, you solve plots of both f and j and work through how the two are related. As you vary w or vary w and b, you end up with different straight lines. And when that straight line passes close to the data, the cost j is small. So the goal of linear regression is to find the parameters w or w and b that results in the smallest possible value for the cost function j. Now, in this video, we work through our example with a simplified problem using only w. In the next video, let's visualize what the cost function looks like for the full version of linear regression using both w and b. And you see some cool 3D plots. Let's go to the next video.
Awesome.
In the last video, you saw one. Visualization of the cost function j of w or j of wb. Let's look at some further, richer visualizations so we can get an even better intuition about what the cost function is doing. Here's what we've seen so far. There's the model's parameters w and b, the cost function j of w and b, as well as the goal of linear regression, which is to minimize the cost function j of w and b over parameters w and b. In the last video, we had temporarily set b to 0 in order to simplify the visualizations. But now let's go back to the original model with both parameters w and b without setting b to be equal to 0. Same as last time, we want to get a visual understanding of the model function f of x, shown here on the left, and how it relates to the cost function j of wb, shown here on the right. Here's a training set of proposed sizes and prices. Let's say we pick one possible function of x, like this one. Here, I've set w to 0.06 and b to 50. So f of x is 0.06 times x plus 50. Note that this is not a particularly good model for this training set. This is actually a pretty bad model that seems to consistently underestimate housing prices. Given these values for W and B, let's look at what the cost function J of W and B may look like. Recall what we saw last time was when you had only W, because we temporarily set B to 0 to simplify things. Back then, we had come up with a plot of the cost function that looked like this as a function of W only. So when we had only one parameter W, the cost function had this U-shaped curve, shaped a bit like a soup. That sounds delicious. Now, in this housing price example that we have on this slide, we have two parameters, W and B. And so the plot becomes a little more complex. It turns out that the cost function also has a similar shape, like a soup bowl, except in 3 dimensions instead of 2. In fact, depending on your training set, the cost function will look something like this. To me, this looks like a soup bowl, maybe because I'm a little bit hungry. Or maybe to you, it looks like a curved dinner plate, or a hammock. Actually, that sounds relaxing too, and there's your coconut drink. Maybe when you're done with this course, you should treat yourself to vacation and relax in a hammock like this. What you see here is a 3D surface plot where the axes are labeled W and B. So as you vary W and B, which are the two parameters of the model, you get different values for the cost function J of W and B. This is a lot like the U-shaped curve you saw in the last video, except instead of having one parameter, W as input in J, you now have two parameters, W and B, as inputs into this soup bowl or this hammock-shaped function J. And I just want to point out that any single point on the surface represents a particular choice of W and B. For example, if W was minus 10 and B was minus 15, then the height of the surface above this point is the value of J when W is minus 10 and B is minus 15. Now, in order to look even more closely at specific points, there's another way of plotting the cost function J that would be useful for visualization, which is rather than using these 3D surface plots, I'd like to take this exact same function J, so I'm not changing the function J at all, and plot it using something called a contour plot. And if you've ever seen a topographical map showing how high different mountains are, the contours in a topographical map are basically horizontal slices of the landscape of, say, a mountain. This image is of Mount Fuji in Japan. I still remember my family visiting Mount Fuji when I was a teenager. It's a beautiful sight. And if you fly directly above the mountain, that's what this a 3D surface shaped, but it is actually a bow just very stretched out, which is why it looks like that. In an optional lab that is shortly to follow, you'll be able to see this in 3D and spin around the surface yourself, and it will look more obviously bow-shaped there. Next, here on the upper right is a contour plot of this exact same cost function as that shown at the bottom. The two axes on this contour plot are B on the vertical axis and W on the horizontal axis. What each of these ovals, also called ellipses, shows is the set of points on the 3D surface which are at the exact same height. In other words, the set of points which have the same value for the cost function J. So to get a contour plot, you take the 3D surface at the bottom and you use a knife to slice it horizontally. You take horizontal slices of that 3D surface and get all the points that are at the same height. Therefore, each horizontal slice ends up being shown as one of these ellipses or one of these ovals. So concretely, if you take that point and that point and that point, all of these 3 points have the same value for the cost function J, even though they have different values for W and B. And in the figure on the upper left, you see also that these 3 points correspond to different functions F, all 3 of which are actually pretty bad for predicting housing prices in this case. Now, the bottom of the bow, where the cost function J is at a minimum, is this point right here, at the center of this concentric ovals. If you haven't seen contour plots much before, I'd like you to imagine, if you will, that you're flying high up above the bow in an airplane or in a rocket ship, and you're looking straight down at it. So that is as if you set your computer monitor flat on your desk facing up, and the bow shape is coming directly out of your screen, rising above your desk. Imagine that the bow shape grows out of your computer screen lying flat, like that. So that each of these ovals have the same height above your screen, and the minimum of the bow is right down there in the center of the smallest oval. So it turns out that the contour plots are a convenient way to visualize the 3D cost function J, but in a way it's plotted in just 2D. In this video, you saw how the 3D bow-shaped surface plot can also be visualized as a contour plot. Using this visualization tool, in the next video, let's visualize some specific choices of W and B in a linear regression model, so you can see how these different choices affect the straight line you're fitting to the data. Let's go on to the next video. Let's look at some more visualizations of W and B. Here's one example. Over here, you have a particular point on the graph J. For this point, W equals about negative 0.15 and B equals about 800. So this point corresponds to one pair of values for W and B that yields a particular cost J. And in fact, this particular pair of values for W and B corresponds to this function, f of x, which is this line that you can see on the left. This line intersects the vertical axis at 800 because B equals 800, and the slope of the line is negative 0.15 because W equals negative 0.15. Now, if you look at the data points in the training set, you will notice that this line is not a good fit to the data. For this function f of x, with these values of W and B, many of the predictions for the value of y are quite far from the actual target value of y that is in training data. Because this line is not a good fit, if you look at the graph of J, the cost of this line is out here. which is pretty far from the minimum. It's a pretty high cost because this choice of W and B is just not that good a fit to the training set. Now, let's look at another example with a different choice of W and B. Now, here's another function that is, still not a great fit for the data, but maybe slightly less bad. So this point here represents the cost for this little pair of W and B that creates that line. The value of W is equal to 0, and the value of B is about 360. This pair of parameters corresponds to this function, which is a flat line because f of x equals 0 times x plus 360. I hope that makes sense. Let's look at yet another example. Here's one more choice for W and B, and with these values, you end up with this line f of x. Again, not a great fit to the data. It's actually further away from the minimum compared to the previous example. And remember that the minimum is at the center of that smallest ellipse. Last example, if you look at f of x on the left, this looks like a pretty good fit to the training set. You can see on the right, this point representing the cost is very close to the center of the small ellipse. It's not quite exactly the minimum, but it's pretty close. For this value of W and B, you get this line f of x. You can see that if you measure the vertical distances between the data points and the predicted values on the straight line, you get the error for each data point. The sum of squared errors for all of these data points is pretty close to the minimum possible sum of squared errors among all possible straight line fits. I hope that by looking at these figures, you can get a better sense of how different choices of the parameters affect the line f of x and how this corresponds to different values for the cost j. And hopefully, you can see how the better fit lines correspond to points on the graph of j that are closer to the minimum possible cost for this cost function j of w and b. In the optional lab that follows this video, you get to run some code. And remember, all the code is given, so you just need to hit Shift-Enter to run it and take a look at it. And the lab will show you how the cost function is implemented in code. And given a small training set and different choices for the parameters, you'll be able to see how the cost varies depending on how well the model fits the data. In the optional lab, you also can play with an interactive contour plot. Check this out. You can use your mouse cursor to click anywhere on the contour plot, and you're going to see the straight line defined by the values you chose for the parameters W. So let's go to the next video to dive into this really important algorithm called gradient descent.
Linear regression the model. Which is the formula that puts
Welcome back. In the last video, we saw visualizations of the cost function j and how you can try different choices of the parameters w and b and see what cost value that gets you. It would be nice if we had a more systematic way to find the values of w and b that result in the smallest possible cost j of wb. It turns out there's an algorithm called gradient descent that you can use to do that. Gradient descent is used all over the place in machine learning, not just for linear regression, but for training, for example, some of the most advanced neural network models, also called deep learning models. Deep learning models are something we learn about in the second course. So learning this tool of gradient descent will set you up with one of the most important building blocks in machine learning. Here's an overview of what we'll do with gradient descent. You have the cost function j of wb right here that you want to minimize. In the example we've seen so far, this is a cost function for linear regression, but it turns out that gradient descent is an algorithm that you can use to try to minimize any function, not just the cost function for linear regression. Just to make this discussion on gradient descent more general, it turns out that gradient descent applies to more general functions, including other cost functions that work with models that have more than two parameters. So, for instance, if you have a cost function j as a function of w1, w2, up to wn and b, your objective is to minimize j over the parameters w1 to wn and b. In other words, you want to pick values for w1 through wn and b that gives you the smallest possible value of j. It turns out that gradient descent is an algorithm that you can apply to try to minimize this cost function j as well. What you're going to do is just start off with some initial guesses for w and b. In linear regression, it won't matter too much what the initial values are, so a common choice is to set them both to 0. So, for example, you can set w to 0 and b to 0 as the initial guess. With the gradient descent algorithm, what you're going to do is you'll keep on changing the parameters w and b a bit every time to try to reduce the cost j of wb until hopefully j settles at or near a minimum. One thing I should note is that for some functions j that may not be a bow shape or a hammer shape, it is possible for there to be more than one possible minimum. Let's take a look at an example of a more complex surface plot j to see what gradient descent is doing. This function is not a squared error cost function. For linear regression with the squared error cost function, you always end up with a bow shape or a hammer shape. But this is the type of cost function you might get if you're training a neural network model. Notice the axes. That is w and b on the bottom axes. For different values of w and b, you get different points on this surface j of wb, where the height of the surface at some point is the value of the cost function. Now, let's imagine that this surface plot is actually a view of a slightly hilly outdoor park or a golf course, where the high points are hills and the low points are valleys, like so. And I'd like you to imagine, if you will, that you're physically standing at this point on the hill. And if it helps you to relax, imagine that there's lots of really nice green grass and butterflies and flowers. It's a really nice hill. And your goal is to start up here and get to the bottom of one of these valleys as efficiently as possible. So what the gradient descent algorithm does is you're going to spin around 360 degrees and look around and ask yourself, if I were to take a tiny little baby step in one direction, and I want to go downhill as quickly as possible toward one of these valleys, what direction do I choose to take that baby step? Well, if you want to walk down this hill as efficiently as possible, it turns out that if you're standing at this point in the hill and you look around, you may notice that the best direction to take your next step downhill is roughly that direction. Mathematically, this is the direction of steepest descent. And it means that when you take a tiny baby little step, this takes you downhill faster than a tiny little baby step you could have taken in any other direction. So after taking this first step, you're now at this point on the hill over here. Now let's repeat the process. Standing at this new point, you're going to again spin around 360 degrees and ask yourself, in what direction would I take the next little baby step in order to move downhill? And if you do that and take another step, you end up moving a bit in that direction, and you can keep going. From this new point, you can again look around and decide what direction would take you downhill most quickly. Take another step, and so on, until you find yourself at the bottom of this valley at this local minimum right here. What you just did was go through multiple steps of gradient descent. It turns out gradient descent has an interesting property. Remember that you can choose a starting point at the surface by choosing starting values for the parameters w and b. When you performed gradient descent a moment ago, you had started at this point over here, right? Now, imagine if you try gradient descent again, but this time you choose a different starting point by choosing parameters that place your starting point just a couple steps to the right over here. If you then repeat the gradient descent process, which means you look around, take a little step in the direction of steepest descent, so you end up here, then you again look around, take another step, and so on. And if you were to run gradient descent the second time, starting just a couple steps to the right of where we did it the first time, then you end up in a totally different valley, this different minimum over here on the right. The bottoms of both the first and the second valleys are called local minima, because if you start going down the first valley, gradient descent won't lead you to the second valley. And the same is true if you started going down the second valley. You would stay in that second minimum and not find your way into the first local minimum. So this is an interesting property of the gradient descent algorithm, and we'll see more about this later. So in this video, you saw how gradient descent helps you go downhill. In the next video, let's look at the mathematical expressions that you can implement to make gradient descent work. Let's go on to the next video. Let's take a look at how you can actually implement the gradient descent algorithm. Let me write down the gradient descent algorithm. Here it is. On each step, w, the parameter, is updated to the old value of w minus alpha times this term d over dw with the cost function j of wb. So what this expression is saying is, update your parameter w by taking the current value of w and adjusting it a small amount, which is this expression on the right, minus alpha times this term over here, okay? So if you feel like there's a lot going on in this equation, it's okay, don't worry about it, we'll unpack it together. First, this equal notation here. Notice I said we're assigning w a value using this equal sign. So in this context, this equal sign is the assignment operator. Specifically, in this context, if you write code that says a equals c, it means take the value of c and store it in your computer in the variable a. Or if you write a equals a plus 1, it means set the value of a to be equal to a plus 1, or increment the value of a by 1. So the assignment operator in coding is different than truth assertions in mathematics, where if I write a equals c, I'm certain, that is, I am claiming that the values of a and c are equal to each other. And hopefully I will never write a truth assertion a equals a plus 1, because, that just can't possibly be true. So in Python and in other programming languages, truth assertions are sometimes written as equals equals. So you may see code that says a equals equals c if you're testing whether a is equal to c. But in application, as we conventionally use it, like in these videos, the equal sign can be used for either assignment or for truth assertion. And so I try to make sure it's clear when I write an equal sign, whether we're assigning a value to a variable or whether we're asserting the truth of the equality of two values. Now, let's dive more deeply into what the symbols in this equation means. The symbol here is the Greek alphabet alpha, and in this equation, alpha is also called the learning rate. The learning rate is usually a small positive number between 0 and 1, and it might be, say, 0.01. What alpha does is it basically controls how big of a step you take downhill. So if alpha is very large, then that corresponds to a very aggressive gradient descent procedure where you're trying to take huge steps downhill. And if alpha is very small, then you'll be taking small baby steps downhill. We'll come back later to delve more deeply into how to choose a good learning rate alpha. And finally, this term here, that's the derivative term of the cost function j. Let's not worry about the details of this derivative right now, but later on you get to see more about the derivative term. But for now, you can think of this derivative term that I drew a magenta box around as telling you in which direction you want to take your baby step, and in combination with the learning rate alpha, it also determines the size of the steps you want to take downhill. Now, I do want to mention that derivatives come from calculus, and even if you're unfamiliar with calculus, don't worry about it. Even without knowing any calculus, you'll be able to figure out all you need to know about this derivative term in this video and the next. One more thing. Remember your model has two parameters, not just w, but also b. So you also have an assignment operation to update the parameter b that looks very similar. B is assigned the old value of b minus the learning rate alpha times this slightly different derivative term d over db of j of wb. So remember in the graph of the surface plot, where you're taking baby steps until you get to the bottom of the valley? Well, for the gradient descent algorithm, you're going to repeat these two update steps until the algorithm converges. And by converges, I mean that you reach the point at a local minimum where the parameters w and b no longer change much with each additional step that you take. Now, there's one more subtle detail about how to correctly implement gradient descent. You're going to update two parameters, w and b, right? So this update takes place for both parameters, w and b. One important detail is that for gradient descent, you want to simultaneously update w and b, meaning you want to update both parameters at the same time. What I mean by that is that in this expression, you're going to update w from the old w to a new w, and you're also updating b from its old value to a new value of b. And the way to implement this is to compute the right side, computing this thing for w and b, and simultaneously at the same time, update w and b to the new values. So let's take a look at what this means. Here's the correct way to implement gradient descent, which does a simultaneous update. This sets a variable temp w equal to that expression, which is w minus that term here. Let's also set another variable temp b to that, which is b minus that term. So you compute both right-hand sides, both updates, and store them into variables temp w and temp b. Then you copy the value of temp w into w, and you also copy the value of temp b into b. Now, one thing you may notice is that this value of w is from before w gets updated. Here, notice that the pre-update w is that this value of w is from before w gets updated. Here, notice that the pre-update w is what goes into the derivative term over here, okay? In contrast, here's incorrect implementation of gradient descent that does not do a simultaneous update. In this incorrect implementation, we compute temp w, so far that's okay. And now here's where things start to differ. We then update w with the value in temp w before calculating the new value for the other parameter b. Next, we calculate temp b as b minus that term here, and finally, we update b with the value in temp b. The difference between the right-hand side and left-hand side implementations is that if you look over here, this w has already been updated to this new value, and it's this updated w that actually goes into the cost function j of wb. It means that this term here on the right is not the same as this term over here that you see on the left. And that also means this temp b term on the right is not quite the same as the temp b term on the left, and thus this updated value for b on the right is not the same as this updated value for variable b on the left. The way that gradient descent is implemented in code, it actually turns out to be more natural to implement it the correct way with simultaneous updates. When you hear someone talk about gradient descent, they always mean the gradient descent where you perform a simultaneous update of the parameters. If, however, you were to implement non-simultaneous update, it turns out it will probably work more or less anyway, but doing it this way isn't really the correct way to implement it. It's actually some other algorithm with different properties. So I would advise you to just stick to the correct simultaneous update and not use this incorrect version on the right. So that's gradient descent. In the next video, we'll go into details of the derivative term, which you saw in this video, but that we didn't really talk about in detail. Derivatives are part of calculus, and again, if you're not familiar with calculus, don't worry about it. You won't need to know calculus at all in order to complete this course or this specialization, and you have all the information you need in order to implement gradient descent. Coming up in the next video, we'll go over derivatives together, and you come away with the intuition and knowledge you need to be able to implement and apply gradient descent yourself. I think that'll be an exciting thing for you to know how to implement. So let's go on to the next video to see how to do that. Now let's dive more deeply into gradient descent to gain better intuition about what it's doing and why it might make sense. Here's the gradient descent algorithm that you saw in previous video. And as a reminder, this variable, this Greek symbol alpha, is the learning rate. And the learning rate controls how big of a step you take when updating the model's parameters w and b. So this term here, this d over dw, this is a derivative term. And by convention in math, this d is written with this funny font here. And in case anyone watching this as a PhD in math or as an expert in multivariate calculus, they may be wondering, that's not, this d is written, this is a derivative term. And by convention in math, this d is written with this funny font here. And in case anyone watching this as a PhD in math or as an expert in multivariate calculus, they may be wondering, that's not the derivative, that's the partial derivative. And yes, to be right. But for the purposes of implementing a machine learning algorithm, I'm just going to call it derivative. And don't worry about these little distinctions. So what we're going to focus on now is get more intuition about what this learning rate and what this derivative are doing and why, when multiplied together like this, it results in updates to parameters w and b that make sense. In order to do this, let's use a slightly simpler example where we work on minimizing just one parameter. So let's say that you have a cost function j of just one parameter w, where w is a number. This means that gradient descent now looks like this. W is updated to w minus the learning rate alpha times d over dw of j of w. And you're trying to minimize the cost by adjusting the parameter w. So this is like our previous example where we had temporarily set b equal to 0. With one parameter w instead of 2, you can look at two-dimensional graphs of the cost function j instead of three-dimensional graphs. Let's look at what gradient descent does on this function j of w. Here on the horizontal axis is parameter w, and on the vertical axis is the cost j of w. Now let's initialize gradient descent with some starting value for w. Let's initialize it at this location. So imagine that you start off at this point right here on the function j. What gradient descent will do is it will update w to be w minus learning rate alpha times d over dw of j of w. Let's look at what this derivative term here means. A way to think about the derivative at this point on the line is to draw a tangent line, which is a straight line that touches this curve at that point. In math, the slope of this line is the derivative of the function j at this point. And to get the slope, you can draw a little triangle like this. And if you compute the height divided by the width of this triangle, that is the slope. So, for example, the slope might be, 2 over 1, for instance. And when the tangent line is pointing up and to the right, the slope is positive, which means that this derivative is a positive number, so is greater than 0. And so the updated w is going to be w minus the learning rate times some positive number. The learning rate is always a positive number. So if you take w minus a positive number, you end up with a new value for w that is smaller. So on the graph, you're moving to the left. You're decreasing the value of w. And you may notice that this is the right thing to do if your goal is to decrease the cost j, because when we move toward the left on this curve, the cost j decreases and you're getting closer to the minimum for j, which is over here. So far, gradient descent seems to be doing the right thing. Now, let's look at another example. Let's take the same function j of w as above, and now let's say that you initialize gradient descent at a different location. Say by choosing a starting value for w that's over here on the left. So that's this point of the function j. Now, the derivative term, remember, is d over dw of j of w. And when we look at the tangent line at this point over here, the slope of this line is the derivative of j at this point. But this tangent line is sloping down into the right. And so this line sloping down into the right has a negative slope. In other words, the And so this means you subtract from w a negative number, but subtracting a negative number means adding a positive number. And so you end up increasing w because subtracting a negative number. So when you update w, you get w minus the learning rate times a negative number. And so this means you subtract from w a negative number, but subtracting a negative number means adding a positive number. And so you end up increasing w because subtracting a negative, so you end up times a negative number. And so this means you subtract from w a negative number, but subtracting a negative number means adding a positive number. And so you end up increasing w because subtracting a negative number is the same as adding a positive number to w. So this step of gradient descent causes w to increase, which means you're moving to the right of the graph, and your cost j has decreased down to here. And again, it looks like gradient descent is doing something reasonable. It's getting you closer to the minimum. So hopefully, these last two examples show some of the intuition behind what the derivative term is doing and why this helps gradient descent change w to get you closer to the minimum. I hope this. Video gave you some sense of why the derivative term in gradient descent makes sense. One other key quantity in the gradient descent algorithm is the learning rate alpha. How do you choose alpha? What happens if it's too small, or what happens if it's too big? In the next video, let's take a deeper look at the parameter alpha to help build intuitions about what it does, as well as how to make a good choice for a good value of alpha for your implementation of gradient descent. The choice of the learning rate alpha will have a huge impact on the efficiency of your implementation of gradient descent. And if alpha, the learning rate, is chosen poorly, gradient descent may not even work at all. In this video, let's take a deeper look at the learning rate. This will also help you choose better learning rates for your implementations of gradient descent. So here again is the gradient descent rule. W is updated to be W minus the learning rate alpha times the derivative term. To learn more about what the learning rate alpha is doing, let's see what can happen if the learning rate alpha is either too small or if it is too large. For the case where the learning rate is too small, here's a graph where the horizontal axis is w and the vertical axis is the cost j. And here's a graph of the function j of w. Let's start gradient descent at this point here. If the learning rate is too small, then what happens is that you multiply your derivative term by some really small number. So you're going to be multiplying by a number alpha that's really small, like 0.000001. And so you end up taking a very small baby step like that. Then from this point, you're going to take another, tiny little baby step. But because the learning rate is so small, the second step is also just minuscule. The outcome of this process is that you do end up decreasing the cost j, but incredibly small. Slowly. So here's another step, and another step, another tiny step, until you finally approach the minimum. But as you may notice, you're going to need a lot of steps to get to the minimum. So to summarize, if the learning rate is too small, then gradient descent will work, but it will be slow. It will take a very long time because it's going to take these tiny baby steps, and it's going to need a lot of steps before it gets anywhere close to the minimum. Now, let's look at the different case. What happens if the learning rate is too large? Here's another graph of the cost function. And let's say we start gradient descent with w at this value here. So it's actually already pretty close to the minimum. So the derivative points to the right, but if the learning rate is too large, then you update w by a giant step to be all the way over here, and that's this point here on the function j. So you move from this point on the left all the way to this point on the right, and now the cost has actually gotten worse. It has increased because it started out at this value here, and after one step, it actually increased to this value here. Now, the derivative at this new point says to decrease w, but when the learning rate is too big, then you may take a huge step going from here all the way out here. So now you've gotten to this point here. And again, if the learning rate is too big, then you take another huge step at the next iteration and way overshoot the minimum again. So now you're at this point on the right, and one more time, you do another update and end up all the way here. And so you're now at this point here. So as you may notice, you're actually getting further and further away from the minimum. So if the learning rate is too large, then gradient descent may overshoot and may never reach the minimum. And another way to say that is that gradient descent may fail to converge and may even diverge. So here's another question you may be wondering. What if your parameter w is already at this point here, so that your cost j is already at a local minimum? What do you think one step of gradient descent will do if you've already reached a minimum? So this is a tricky one. When I was first learning this stuff, it actually took me a long time to figure it out. But let's work through this together. Let's suppose you have some cost function j, and the one you see here isn't a square error cost function. And this cost function has two local minima corresponding to the two values that you see here. Now, let's suppose that That after some number of steps of gradient descent, your parameter w is over here, say equal to 5. And so this is the current value of w. This means that you're at this point on the cost function j, and that happens to be a local minimum. Turns out if you draw a tangent to the function at this point, the slope of this line is 0. And thus, the derivative term here is equal to 0 for the current value of w. And so your gradient descent update becomes w is updated to w minus the learning rate times 0. Where here, that's because the derivative term is equal to 0. And this is the same as saying, let's set w to be equal to w. So this means that if you're already at a local minimum, gradient descent leaves w unchanged because it just updates the new value of w to be the exact same old value of w. So concretely, let's say if the current value of w is 5 and alpha is 0.1, after one iteration, you update w as w minus alpha times 0, and it is still equal to 5. So if your parameters have already brought you to a local minimum, then further gradient descent steps do absolutely nothing. It doesn't change the parameters, which is what you want, because it keeps the solution at that local minimum. This also explains why gradient descent can reach a local minimum even with a fixed learning rate alpha. Here's what I mean. To illustrate this, let's look at another example. Here's a cost. j of w that we want to minimize, let's initialize gradient descent up here at this point. If we take one update step, maybe it'll take us to that point. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large. And so the next update step will not be as large. Gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large. And so the next update step will not be as large as that first step. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is an update step that we want to minimize. Let's initialize gradient descent up here at this point. If we take one update step, maybe it'll take us to that point. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large. And why gradient descent can reach a local minimum, even with a fixed learning rate alpha. Here's what I mean. To illustrate this, let's look at another example. Here's the cost function a of w that we want to minimize. Let's initialize gradient descent up here at this point. If we take one update step, maybe it'll take us to that point. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large. And so the next update step will not be as large as that first step. Now, we're at this third point here, and the derivative is smaller than it was at the previous step, and we'll take an even smaller step. As we approach the minimum, the derivative gets closer and closer to zero. So as we run gradient descent, eventually we're taking very small steps until you finally reach a local minimum. So just to recap, as we get nearer a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, the derivative automatically gets smaller. And that means the update steps also automatically get smaller, even if the learning rate alpha is kept at some fixed value. So that's it.
ఫైనల్ ప్రాసెస్ పాలిషింగ్ కోసం మొదటి మిషన్ మనం చూస్తాం వస్తే ఆ మిషన్ లో తీసిన కలిపి మళ్ళీ ఏం చేస్తాం ఇంకో మిషన్ ఫైన్ టెక్స్చర్ గా వీళ్ళు వస్తే ఇంకో మిషన్ చేస్తారు ఈ మిషన్ ఇంకా కాకపోతే ఫస్ట్ మిషన్ వేసుకోవాలి కాకపోతే ఇక్కడ ఏమవుతుందంటే ఇంకా పైగా నీట్ గా రీసెంట్ వస్తుంది ఇక్కడ ఏమవుతుందంటే ఒక పక్క నుంచి కలిపి వేస్తున్నారు ఒక పక్కన చూస్తే చాలా ఫైన్గా మ్యాంగో జ్యూస్ టైప్ వస్తుంది దీన్ని ప్రోటీన్ కోసం వాడతారు కానీ ప్రోటీన్ కోసం సో ఈ పల్ప్ ఏం చేస్తారంటే ఇప్పుడు జెల్లీ తీసేస్తారు కదండి లాస్ట్ డే అప్పుడు ఏంటంటే పైన పాలిషింగ్ అంటారు
The gradient descent algorithm. You can use it to try to minimize any cost function j, not just the mean squared error cost function that we're using for linear regression. In the next video, we're going to take the function j and set that back to be exactly the linear regression model's cost function, the mean squared error cost function that we come up with earlier. And putting together gradient descent with this cost function, that will give you your first learning algorithm, the linear regression algorithm. The choice of the learning rate alpha will have a huge impact on the efficiency of your implementation of gradient descent. And if alpha, the learning rate, is chosen poorly, gradient descent may not even work at all. In this video, let's take a deeper look at the learning rate. This will also help you choose better learning rates for your implementations of gradient descent. So here again is the gradient descent rule. W is updated to be W minus the learning rate alpha times the derivative term. To learn more about what the learning rate alpha is doing, let's see what could happen if the learning rate alpha is either too small or if it is too large. For the case where the learning rate is too small, here's a graph where the horizontal axis is W and the vertical axis is the cost J. And here's a graph of the function J of W. Let's start gradient descent at this point here. If the learning rate is too small, then what happens is that you multiply your derivative term by some really small number. So you're going to be multiplying by a number alpha that's really small, like 0.000001. And so you end up taking a very small baby step like that. Then from this point, you're going to take another, tiny little baby step. But because the learning rate is so small, the second step is also just minuscule. The outcome of this process is that you do end up decreasing the cost J, but incredibly slowly. So here's another step, and another tiny step, until you finally approach the minimum. But as you may notice, you're going to need a lot of steps to get to the minimum. So to summarize, if the learning rate is too small, then gradient descent will work, but it will be slow. It will take a very long time because it's going to take these tiny baby steps, and it's going to need a lot of steps before it gets anywhere close to the minimum. Now, let's look at a different case. What happens if the learning rate is too large? Here's another graph of the cost function. And let's say we start gradient descent with W at this value here. So it's actually already pretty close to the minimum. So the derivative.
Hello? Were you asleep? Hello? Bruh. Yes. Hmm. Yes, I can hear you. Yes. No, 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 no. No, listen, wait. What didn't you understand? You said something about partial derivatives. Oh, chill. I'm not doing neural networks. Chill. I'm doing linear regression. I'm not doing neural networks. I'm looking at the cost function for linear regression. I'm starting with the course. Bruh. Don't excite. Yeah, yeah. Chill, bro. Chill, bro. Chill. Chill. Let me get to your level, please. But but you understood gradient descent for linear regression, yes? Okay. Yes. 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 Uh, okay. Give me some time. Give me some time. Okay. Okay. Bruh, I don't know, bruh. It's my dad, and he said he's busy, and then I don't want to disturb him. So maybe this weekend, hopefully, or Friday. Yeah. Yeah. I don't know. I will tell my dad. I will tell him. Yeah. Okay. I will. But I forced the 400 and 600 anomalies. I got it. I'm working on that data set. Yeah, I know. But he wanted to see 400 and 600, so he's gonna see just that one. Just uh, I know, I know, I know, I know, I know, I know. But I got 400 and 600. So don't look at it. Don't look at 1,900. Yeah, last week you said you wanted 400 and 600. This week you have it. Yeah, I want to move. Yeah, 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 that's correct. Yes. Yeah. Hopefully we. Mhm. Hopefully we move to multivariate instead of just one column. Yes, yes, this Gaussian. Yes. Yeah, bruh. Yeah. Mm-mm. Yeah, 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 yeah. We will look at it. Hey, hey, bruh. Really? Hey, hey, hey. Stockholm's nice, but I haven't gone out. What do you mean why? To hell now. I'm going out tomorrow. I'm going out tomorrow. I'm going out tomorrow. I'm going out tomorrow. Bro, I'm going. Are you deaf? Chill, 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 chill. Yo go ute imoron. Declar. Yo gor ut imoron. There's a birthday party, so no, no, no. Relax, 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 relax. It's a birthday party, so no, 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 no. It's that weird friend I told you, the guy who was supposed to come there to study. Yeah. No, 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 no. Of course not. Please do come. So let me pull up. Yeah, 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 yeah. Of course, of course, of course. Mm. Oh my- yeah, 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 yeah. I don't want to wake up. Listen, listen. Just one more week. Enjoy your week. Mm. Drugs. Yes, we can. We should. I don't know. Okay, you want me to search for courses? Okay, I can search for courses. All right, all right, all right. Are you thinking about ideas for the Germany competition? So think about an idea then. Yes, 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 yes. So think about an idea and let's work on it. I told you 2 days ago. Okay, okay. How about this? How about this? How about this? By the end of this week, we need to tell each other the ideas. Okay? Yes. Wednesday. Yeah. Yeah. Yes. All right. Yeah. Yeah. I will look at the things. I will look at it and send them to you. Okay. Okay. I don't know. Maybe. Hmm. Yeah. Yeah. Okay. I will look at it then. No. 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 It's just analyzing data. That's it. It's kind of boring. You don't make predictions. Yeah. Mm. Yeah. 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 Of course. Of course. Of course. Of course. Get off my phone. Yeah, 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 yeah. She's in Germany. I told you. You like you dumb. well, well, well. Then tell her. Well, tell her I said hi. Say less. Say less. Bye. 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 Think of the ideas by the end of this week. Pause.
Points to the right, but if the learning rate is too large, then you update W by a giant step to be all the way over here, and that's this point here on the function J. So you move from this point on the left all the way to this point on the right, and now the cost has actually gotten worse. It has increased because it has started out at this value here, and after one step, it actually increased to this value here. Now, the derivative at this new point says to decrease W, but when the learning rate is too big, then you may take a huge step going from here all the way out here. So now you've gotten to this point here. And again, if the learning rate is too big, then you take another huge step at the next iteration and way overshoot the minimum again. So now you're at this point on the right, and one more time, you do another update and end up all the way here. And so you're now at this point here. So as you may notice, you're actually getting further and further away from the minimum. So if the learning rate is too large, then gradient descent may overshoot and may never reach the minimum. And another way to say that is that gradient descent may fail to converge and may even diverge. So here's another question you may be wondering. What if your parameter w is already at this point here, so that your cost j is already at a local minimum? What do you think one step of gradient descent will do if you've already reached a minimum? So this is a tricky one. When I was first learning this stuff, it actually took me a long time to figure it out, but let's work through this together. Let's suppose you have some cost function j, and the one you see here isn't a squared error cost function, and this cost function has two local minima corresponding to the two values that you see here. Now, let's suppose that after some number of steps of gradient descent, your parameter w is over here, say equal to 5, and so this is the current value of w. This means that you're at this point on the cost function j, and that happens to be a local minimum. Turns out if you draw a tangent to the function at this point, the slope of this line is 0, and thus the derivative term here is equal to 0 for the current value of w, and so your gradient descent update becomes w is updated to w minus the learning rate times 0, where here that's because the derivative term is equal to 0. And this is the same as saying let's set w to be equal to w. So this means that if you're already at a local minimum, gradient descent leaves w unchanged because it just updates the new value of w to be the exact same old value of w. So concretely, let's say if the current value of w is 5 and alpha is 0.1, after one iteration, you update w as w minus alpha times 0, and it is still equal to 5. So if your parameters have already brought you to a local minimum, then further gradient descent steps do absolutely nothing. It doesn't change the parameters, which is what you want, because it keeps the solution at that local minimum. This also explains why gradient descent can reach a local minimum, even with a fixed learning rate alpha. That's what I mean. To illustrate this, let's look at another example. Here's the cost function j of w that we want to minimize. Let's initialize gradient descent up here, which is what you want, because gradient descent steps do absolutely nothing. It doesn't change the parameters, which is what you want, because it keeps the solution at that local minimum. This also explains why gradient descent can reach a local minimum, even with a fixed learning rate alpha. Here's what I mean. To illustrate this, let's look at another example. Here's the cost function j of w that we want to minimize. Let's initialize gradient descent up here at this point. If we take one update step, maybe it'll take us to that point. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large. And so the next update step will not be as large as that first step. Now, we're at this third point here, and the derivative is smaller than it was at the previous step, and we'll take an even smaller step. As we approach the minimum, the derivative gets closer and closer to 0. So as we run gradient descent, eventually we're taking very small steps until you finally reach a local minimum. So just to recap, as we get nearer a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, the derivative automatically gets smaller. And that means the update steps also automatically get smaller, even if the learning rate alpha is kept at some fixed value. So that's the gradient descent algorithm. You can use it to try to minimize any cost function j, not just the mean squared error cost function that we're using for linear regression. In the next video, we're going to take the function j and set it back to be exactly the linear regression model's cost function, the mean squared error cost function that we come up with earlier. And putting together gradient descent with this cost function, that will give you your first learning algorithm, the linear regression algorithm. So previously, you took a look at the linear regression model, and then the cost function, and then the gradient descent algorithm. In this video, we're going to put it all together and use the squared error cost function for the linear regression model with gradient descent. This will allow us to train the linear regression model to fit a straight line to our training data. Let's get to it. Here's the linear regression model, and to the right is the squared error cost function, and below is the gradient descent algorithm. It turns out if you calculate these derivatives, these are the terms you would get. The derivative with respect to w is this, 1 over m, sum from I equals 1 through m, then the error term, that is the difference between the predicted and the actual values, times the input feature xi, and the derivative with respect to b is this formula over here, which looks the same as the equation above, except that it doesn't have that xi term at the end. And if you use these formulas to compute these two derivatives and implement gradient descent this way, it will work. Now, you may be wondering, where did I get these formulas from? They're derived using calculus. If you want to see the full derivation, I'll quickly run through the derivation on the next slide. But if you don't remember or aren't interested in the calculus, don't worry about it. You can skip the materials on the next slide entirely and still be able to implement gradient descent and finish this class, and everything will work just fine. So in this slide, which is one of the most mathematical slides of the entire specialization and is completely optional, we'll show you how to calculate the derivative terms. Let's start with the first term, the derivative of the cost function j with respect to w. We'll start by plugging in the definition of the cost function j. So j of wb is this. So 1 over 2m times this sum of the squared error terms. And now remember also that f of wb of xi is equal to this term over here, which is wxi plus b. And so what we would like to do is compute the derivative, also called the partial derivative, with respect to w of this equation right here on the right. If you've taken a calculus class before, and again, it's totally fine if you haven't, you may know that by the rules of calculus, the derivative is equal to this term over here, which is why the 2 here and the 2 here cancel out, leaving us with this equation that you saw on the previous slide. So this, by the way, is why we had defined the cost function with the 1/2 earlier this week, is because it makes the partial derivative neater. It cancels out the 2 that appears from computing the derivative. For the other derivative with respect to b, this is quite similar. I can write it out like this, and once again, plug in the definition of f of xi, giving this equation. And by the rules of calculus, this is equal to this, where there's no xi anymore at the end. And so the 2's cancel once more, and you end up with this expression for the derivative with respect to b. And so now you have these 2 expressions for the derivatives, and you can plug them into the gradient descent algorithm. So here's the gradient descent algorithm for linear regression. You repeatedly carry out these updates to w and b until convergence. Remember that this f of x is a linear regression model, so it's equal to w times x plus b. This expression here is the derivative of the cost function with respect to w, and this expression is the derivative of the cost function with respect to b. And just as a reminder, you want to update w and b simultaneously on each step. Now, let's get familiar with how you do simultaneously on each step. Now, let's get
this is y hat minus y hat minus what the fuck is this?
so it's equal to w times x plus b.
Okay.
This expression here is the derivative of the cost function with respect to w, and this expression is the derivative of the cost function with respect to b. And just as a reminder, you want to update w and b simultaneously on each step. Now, let's get familiar with how gradient descent works. One issue we saw with gradient descent is that it can lead to a local minimum instead of a global minimum, where the global minimum means the point that has the lowest possible value for the cost function j out of all possible points. You may recall this surface plot that looks like an outdoor park with a few hills with the grass and the birds is a relaxing outdoor hill. This function has more than one local minimum. Remember, depending on where you initialize the parameters w and b, you can end up at different local minima. You can end up here, or you can end up here. As it turns out, when you're using a square root cost function with linear regression, the cost function does not and will never have multiple local minima. It has a single global minimum because of this bow shape. The technical term for this is that this cost function is a convex function. Informally, a convex function is a bow-shaped function, and it cannot have any local minima other than the single global minimum. So, when you implement gradient descent on a convex function, one nice property is that so long as your learning rate is chosen appropriately, it will always converge to the global minimum. Congratulations, you now know how to implement gradient descent for linear regression. We have just one last video for this week. In that video, we'll see this algorithm in action. Let's go to that last video. Let's see what happens when you run gradient descent for linear regression. Let's go see the algorithm in action. Here's a plot of the model and data on the upper left, and a contour plot of the cost function on the upper right. And at the bottom is the surface plot of the same cost function. Often w and b will both be initialized to 0, but for this demonstration, let's initialize w to be equal to negative 0.1 and b to be 900. So this corresponds to f of x equals negative 4.1x plus 900. Now, if we take one step using gradient descent, we end up going from this point of the cost function out here to this point, just down and to the right. And notice that the straight line of the model and data on the upper left, and a contour plot of the cost function on the upper right. And at the bottom is the surface plot of the same cost function. Often w and b will both be initialized to 0, but for this demonstration, let's initialize w to be equal to negative 0.1 and b to be 900. So this corresponds to f of x equals negative 4.1x plus 900. Now, if we take one step using gradient descent, we end up going from this point of the cost function out here to this point, just down and to the right. And notice that the straight line fit is also changed a bit. Let's take another step. The cost function has now moved to this third point, and again, the function f of x has also changed a bit. As we take more of these steps, the cost is decreasing at each update. So the parameters w and b are following this trajectory. And if you look on the left, you get this corresponding straight line fit that, fits the data better and better until we've reached the global minimum. The global minimum corresponds to this straight line fit, which is a relatively good fit to the data. I mean, isn't that cool? And so that's gradient descent. And we're going to use this to fit a model to the housing data. And you can now use this f of x model to predict the price of your client's house or anyone else's house. For instance, if your friend's house size is 1,250 square feet, you can now read off the value and predict that maybe they could get, I don't know, $250,000 for the house. To be more precise, this gradient descent process is called batch gradient descent. The term batch gradient descent refers to the fact that on every step of gradient descent, we're looking at all of the training examples instead of just a subset of the training data. So in computing gradient descent, when computing derivatives, we're computing the sum from I equals 1 to m. And batch gradient descent is looking at the entire batch of training examples at each update. I know that batch gradient descent may not be the most intuitive name, but this is what people in the machine learning community call it. If you've heard of the newsletter The Batch that's published by deeplearning.ai, the newsletter The Batch was also named for this concept in machine learning. And then it turns out that there are other versions of gradient descent that do not look at the entire training set, but instead looks at small subsets of the training data at each update step. But we'll use batch gradient descent for linear regression. So that's it for linear regression. Congratulations on getting through your first machine learning model. I hope you go and celebrate, or I don't know, maybe take a nap in your hammock. In the optional lab that follows this video, you see a review of the gradient descent algorithm as well as how to implement it in code. You also see a plot that shows how the cost decreases as you continue training more iterations. And you also see a contour plot, seeing how the cost gets closer to the global minimum as gradient descent finds better and better values for the parameters W and B. So remember that to do the optional lab, you just need to read and run this code. You won't need to write any code yourself. And I hope you take a few moments to do that and also become familiar with the gradient descent code, because this will help you to implement this and similar algorithms in the future yourself. Thanks for sticking with me through the end of this last video for the first week, and congratulations for making it all the way here. You're on your way to becoming a machine learning person. In addition to the optional labs, if you haven't done so yet, I hope you also check out the practice quizzes, which are a nice way that you can double check. You now know how to useful and valuable. Lastly, we'll also go over some practical tips that will really help for getting linear regression to work on practical applications. I'm really happy to have you here with me in this class, and I look forward to seeing you next week. Welcome back. In this week, we'll learn to make Welcome back. In this week, we'll learn to make linear regression much faster and much more powerful. And by the end of this week, you'll be 2/3 of the way to finishing this first course. Let's start by looking at a version of linear regression that can look at not just one feature, but a lot of different features. Let's take a look. In the original version of linear regression, you had a single feature X, the size of the house, and you're able to predict Y, the price of the house. So the model was FWB of X equals WX plus B. But now, what if you did not only have the size of the house as a feature with which to try to predict the price, but if you also knew the number of bedrooms, the number of floors, and the age of the home in years? It seems like this would give you a lot more information with which to predict the price. To introduce a little bit of new notation, we're going to use the variables x subscript 1, x subscript 2, x subscript 3, and x subscript 4 to denote the 4 features. And for simplicity, let's introduce a little bit more notation. We'll write x subscript j, or sometimes I'll just say for short x sub j, to represent the list of features. So here, j will go from 1 through 4 because we have 4 features. I'm going to use lowercase n to denote the total number of features. So in this example, n is equal to 4. As before, we'll use x superscript I to denote the ith training example. So here, x superscript I is actually going to be a list of 4 numbers, or sometimes we'll call this a vector that includes all the features of the ith training example. So as a concrete example, x superscript in parentheses 2 will be a vector of the features for the second training example. So it will equal to this 1, 4, 1, 6, 3, 2, and 40. And technically, I'm writing these numbers in a row, so sometimes this is called a row vector rather than a column vector. But if you don't know what the difference is, don't worry about it. It's not that important for this purpose. And to refer to a specific feature in the I training example, I will write x superscript I subscript j. So for example, x superscript 2 subscript 3 will be the value of the third feature, that is the number of floors in the second training example, and so that's going to be equal to 2. Sometimes, in order to emphasize that this x2 is not a number, but it's actually a list of numbers, that is a vector, we'll draw an arrow on top of that, just to visually show that is a vector, and over here as well. But you don't have to draw this arrow in your notation. You can think of the arrow as an optional signifier that's sometimes used just to emphasize that this is a vector and not a number. Now that we have multiple features, let's take a look at what our model would look like. Previously, this is how we defined the model, where x was a single feature, so a single number. But now, with multiple features, we're going to define it differently. Instead, the model will be f wb of x equals w1x1 plus w2x2 plus w3x3 plus w4x4 plus b. Concretely, for housing price prediction, one possible model may be that we estimate the price of the house as 0.1 times x1, the size of the house, plus 4 times x2, the number of bedrooms, plus 10 times x3, the number of floors, minus 2 times x4, the age of the house in years, plus 80. Let's think a bit about how you might interpret these parameters. If the model is trying to predict the price of the house in thousands of dollars, you can think of this b equals 80 as saying that the base price of the house starts off at maybe $80,000, assuming it has no size, no bedrooms, no floor, and no age. And you can think of this 0.1 as saying that maybe for every additional square foot, the price will increase by $0.1 thousand or by $100, because we're saying that for each square foot, the price increases by 0.1, times $1,000, which is $100. And maybe for each additional bathroom, the price increases by $4,000. And for each additional floor, the price may increase by $10,000. And for each additional year of the house's age, the price may decrease by $2,000 because the parameter is -2. And in general, if you have n features, then the model will look like this. Here again is the definition of the model with n features. What we're going to do next is introduce a little bit of notation to rewrite this expression in a simpler but equivalent way. Let's define w as a list of numbers that list the parameters w1, w2, w3, all the way through wn. In mathematics, this is called a vector. And sometimes to designate that this is a vector, which just means a list of numbers, I'm going to draw a little arrow on top. You don't always have to draw this arrow, and you can do so or not in your own notation. So you can think of this little arrow as just an optional signifier to remind us that this is a vector. If you've taken a linear algebra class before, you might recognize that this is a row vector as opposed to a column vector. But if you don't know what those terms mean, you don't need to worry about it. Next, same as before, b is a single number, not a vector. And so this vector w together with this number b are the parameters of the model. Let me also write x as a list or a vector, again, a row vector, that lists all of the features x1, x2, x3, up through xn. This is, again, a vector, so I'm going to add a little arrow up on top to signify. So in the notation up on top, we can also add little arrows here and here to signify that that w and that x are actually these lists of numbers. They're actually these vectors. So with this notation, the model can now be rewritten more succinctly as f of x equals the vector w dot, and this dot refers to dot product from linear algebra of x, the vector, plus the number b. So what is this dot product thing? Well, the dot product of two vectors, of two lists of numbers, w and x, is computed by taking the corresponding pairs of numbers, w1 and x1, multiplying that, w2, x2, multiplying that, w3, x3, multiplying that, all the way up to wn, xn, multiplying that, and then summing up all of these products. Writing that out, this means that the dot product is equal to w1, x1 plus w2, x2 plus w3, x3.
Awesome. What do
plus all the way up to wn, xn. And then finally, we add back in the b on top. And you notice that this gives us exactly the same expression as we had on top. So the dot product notation lets you write the model in a more compact form with fewer characters. The name for this type of linear regression model with multiple input features is multiple linear regression. This is in contrast to univariate regression, which had just one feature. And by the way, you might think this algorithm is called multivariate regression, but that term actually refers to something else that we won't be using here. So I'm going to refer to this model as multiple linear regression.
Yeah.
And so that's it for linear regression with multiple features, which is also called multiple linear regression. In order to implement this, there's a really neat trick called vectorization, which will make it much simpler to implement this and many other learning algorithms. Let's go on to the next video to take a look at what is vectorization. In this video,